Hey everybody, welcome to 8.3 Part 2. By the way, I was reviewing my 8.3 Part 1 video and did anybody count how many times I said the word so in that video? I thought that was pretty funny, so you can make fun of me for that tomorrow. I'll try to cut that down for this video. Our first example here is just actually a continuation of what we did on the front side. So the first two graphs are just like what we did on the front side. So if you feel up to the challenge, pause the video and go ahead and try these two. Alright, if you have unpaused right now, for the first graph, remember step 1, plot your y-intercept. In this situation that is 2. For our second point, I'm going to find another point. I'm going to use x is 1. When I plug that in, I end up with a point of 4.23. 2, 3, 4. Draw in my graph. And I didn't tell you to do this, so you may not have done this already, but let's find the asymptote and the domain and range. So the asymptote is still at y equals 0. It has not shifted up or down at all. And this is an exponential graph, like I said earlier, just like all exponential graphs we've done in 8.1 and 8.2. So the domain is all reals. The range, this is above the y equals 0 line, so it's going to be y is greater than 0. Alright, let's check your work for part B. First of all, it doesn't really have a y-intercept, though it has that negative right there, so that means that the y-intercept is at -1. When I find my other point, I type this into my calculator, and you should end up with -0.02. And so my graph looks something like that. Quick troubleshooting tip, if you keep getting the wrong number here for your second point, double check this, because according to order of operations, we have to multiply this together. We want that whole thing as part of the exponent. So in your calculator, that should be together. Of course, I hope you do not have to type in -4 times 1, but if you do, it should look like that. Let's do the domain, range, and asymptote for this one. So my asymptote has not shifted. It's still at y equals 0 this time. My domain is still all reals, like all exponential graphs. And my range, this time it is below that line. That means that y is less than 0. Let's move on to some where we have to do up, down, right, left shifts. I'm going to teach this like what I did in 8.1 and 8.2, which means I'm going to graph it first without the shift, and then I'm going to shift it. And only your final answer is required, so if you do not want to graph the original one, you do not have to. When I say that I want to shift or graph the original without the shift, in this situation I mean just this part of it. So what I would do is first graph y equals 3 times e to the 2x, and let's go through that quick. So y-intercept is 3. Oh, and one quick comment. This graph, when I do point 2, I actually end up getting 22.2. So we're going to have to make the scale on my graph different than normal. So I'm going to make the scale on my graph up by 5, 10, 15. So actually each tick mark is 2.5, which might make things a struggle in a second, but whatever, we'll figure it out. So my y-intercept is at 3, and the second point is at 1, 22.2, so something like that. Alright, this is my graph without the shifts. So that just represents y equals 3 times e to the 2x. Now I'm going to do the shift. So step 1, graph it without the shift. Step 2, shift it. According to these rules that I gave you on the other side and from 8.1 and 8.2, I see a minus sign, so that means right 1, and I see a plus sign, so that means up 2. So each point I'm going to go right 1, up 2. And I have not yet labeled the x-axis, so I wrote stuff down without even saying anything. I'm assuming right now that the x-axis is labeled normally. Alright, we're going to go right 1, up 2 for each one of the points then. Right 1, up to just do the best you can. And then because I've moved up, my asymptote also has shifted up. So make sure you draw in your new asymptote. And that's the line that I can use as a guide when I'm making my final answer now. So I know that the tail goes right along that asymptote. I'm going to now find my domain and range. It's still an exponential graph. Domain is still all reals. I'll give you a second. What do you think the range is? What do you think the range is based off of what we have done? I hope that you're kind of becoming an expert at this right now. Oh, you know what? I just made a mistake. I made 2 mistakes, really. Do you see it? Okay. The asymptote, it actually went up 2, so my asymptote should be at 2. And then the other mistake I made was I graphed it as if the scale was 1, 2, 3, 4, 5, but it's not. The scale goes up by 5. So y equals 2 is a line kind of like right here, actually. That probably does not really change your picture because that graph is so tight right there anyways, but I'm glad that I've caught that mistake. Did you come up with the range? The reason I thought of that mistake was I was thinking, oh, it goes up 2, so the range should be up 2, but my asymptote I had incorrect. That's how I realized that. All right, pause the video and try the next one on your own. If you are ready to listen to the next one, here's what I'm going to do. First, I'm going to graph it without the shifts. And when I graphed it, I found a y-intercept of 0, 1/4. And I found my other point. It's very, very small, so this is a difficult one to plot. I actually ended up with 0.01. So I just plugged in the 1 in for the x here, and I used my calculator. But that is going to be kind of even hard to draw, but there it is. Do the best you can. So this was my graph without the shifts, so that is not my final answer. Next, I do not have a left or right shift because there is no k or h value, but there is a down 1 there for that k value. So this is going to be shifted down 1. I'll draw in my asymptote first, and then each one of these dots I'll shift down 1, down 1. And again, do the best you can to draw in the graph. There is my final answer. Asymptote is at y equals -1. Domain, all reals. Range, y is greater than -1. Please write down any questions you have on that and pause the video. Make sure you have that all written down. When you're ready, move on to the next section. Next, we're going to show you how E applies to interest and finance. So the thing is, remember yesterday, or in section 8.2, we had this formula. All right. Okay, I'm struggling here. So I had the principal 1 plus r over n to the nt power. Now this part right here is what's going to get replaced by E, because basically what I tried to show you on the front page was that as n gets bigger and bigger and bigger, this number in here gets closer and closer and closer to E. So we're going to be talking about something called the continuously compounding interest formula, and imagine yourself trying to compound interest continuously. So if I asked you how many times per year has my interest been compounded, even if it was once every second for the whole year, that would be a huge number for n. So E replaces that part of it. My formula looks like this then. A equals P times E to the RT. So again, this whole part just got replaced by E. Some students like to call this the PERT formula to remember it, because it looks like the word PERT. Okay, P is still the principal. And R, or starting amount, I think on 8.2 I called it the starting amount. R is still the rate as a decimal. And for this formula specifically, T is always in years. You might remember the other day when we had this, the general formula. I'm forgetting what variable we used, but something like that. Remember I said t doesn't have to be years? For this formula, t does have to be years. So specifically the formula was created that way. So if you get something like 6 months, use 0.5 in the formula. So here's a few examples of this. You deposit $1,000 in an account that pays 8% annual interest compounded continuously. What is the balance after 1 year? So this is actually quite an easy problem, but the thing is, when you test on this, you're going to have to be able to identify this and know that if it says compounded continuously, you're going to specifically use this formula. So I'm going to go ahead, plug in my starting amount, plug in my interest as a decimal, and I'm going to plug in my time. And note, these have to be multiplied together when you're typing it into your calculator. So let's say that I want to type this in my calculator all at the same time. Now, you don't need to type in ×1, but if it was a different number and you needed to use it, you want to put that together in the parentheses. You should end up with $1,083.29. Why don't you type that in and make sure you can get it correct. The next one, go ahead and try on your own quick. If you have unpaused and you're with me now, here's your setup. And for a final answer, you should have ended up with $1,530.30. Here's another application. Sometimes they give you a formula already. So for this last example on our notes sheet today, it says, since 1972, the U.S. Fish and Wildlife Service has kept a list of endangered species in the United States. For years 1972 through 1998, the number S of species on the list can be modeled by this equation, where T is the number of years since 1972. That's important. All right. They gave us a formula this time, and now we're going to use that in some situations. First of all, what was the number of endangered species in 1972? In disguise, 1972 is our starting year, right? So in disguise are asking us, what was the starting number? And we know the starting number in our formula comes before the E. So we can't have 0.6 of a species, but that must be some average or something. So approximately 119.6 species in 1972. Next question, what was the number in 1980? So first I got to ask myself, how many years past 1972 is this? It is 8 years past 1972. That means T is 8. I am going to use the formula and plug in an 8 for T. And again, this is what I was saying earlier, where you got to make sure that this 0.0, both of these parts in the exponent are multiplied together in the parentheses there. But now if you type that into your calculator, you should end up with 249.07. So let's say approximately 249 species. So it's kind of sad that in 8 years during that time period it increased to 249 species that were endangered in the US alone. All right, part C, estimate when the number of endangered species reached 1,000. Okay, so this is like what we did. We've hopefully done a few of these by now. This time they gave me the ending amount. So I'm going to take my ending amount, the S in my formula, and this time T is the missing variable. And in order to do this, at this point we don't know how to solve this yet, so we're going to do some guessing and checking. And when I think about this, we know that 8 years was 249. So let's be smart about this here. 8 years was 249. So I'm not going to guess 9 right away because I don't think it's going to be 9. Maybe 15. And I don't know, I actually didn't do this one ahead of time. Usually I'm very prepared, not this time. So I'm going to just guess and check and see what we get here. And actually I'm almost out of time, so I'm just going to tell you we should get approximately 23 to 24 years. So that was 1995 to 1996. Okay, thanks for listening. Talk to you next time.